Okay. So now I would like to welcome you all for the second part of this session. So the first speaker of this second part is Dr. Nashim Akhtar, Assistant Professor at Department of Mathematics, Presidency University College, Kolkata, India. So the title of his talk is Fractal Interpolation Functions on Non-Euclidean Projective Space. So now I would like to welcome the professor to begin his talk. So over to you, Professor. Thank you.
Okay, thank you, Megha, for organizing this session. So is it visible, that screen?
Yes, yes.
Okay. So the title of my talk is that fractal interpolation functions on non-Euclidean projective space. So that Barnsley actually introduced that construction of fractal interpolation functions on Euclidean plane in R2. Then after that, there are many works has been carried out on that direction for construction of various type of fractal interpolation functions on various Euclidean spaces. Recently, Barnsley et al. They have introduced one concept that is known as real projective iterated function system, and on that article they also mentioned that by suitably modeling that iterated function system, one can construct that is non-smooth fractal interpolation functions. So motivated from that work of Barnsley et al., we have constructed fractal interpolation functions on non-Euclidean projective space. Okay. So this is the preliminaries that RP2 is a quotient of the set R3 minus 0 of non-zero vectors by the equivalence relation x related to y if and only if x equals to lambda y for some non-zero reals lambda. Okay, so that is one may think that this is a collection of all lines passing through the origin without this 0 point. Okay, so for any x in R3 minus 0, one can define box x as x1 colon x2 colon x3 as the equivalence class containing x. That is nothing but the line passing through 0. So next is hyperplane. So if PQ belongs to RP2, have the homogeneous coordinates P1, P2, P3 and Q1, Q2, Q3 respectively, so that summation PK, QK equals to 0, then one can say that P is orthogonal to Q and write P perpendicular to Q. And a hyperplane in RP2 is a set of all Q which are perpendicular to P, and that is denoted as HP, and which is a subspace of RP2. For example, that if you take that 001 in RP2, that is actually the z-axis one may think of in R3. So that hyperplane perpendicular to that is nothing but that xy plane. Here actually that all those lines which are on that xy planes. Next is that real projective iterated function system. So first we define that is projective transformation. So if for A belongs to GL3R, that is the set of all 3 by 3 invertible real matrices, then the projective transformation WA is given by WA from RP to RP2 with WAX equals to AX. That is the equivalence class of AX. That is AX. That is the lines passing through that AX on methane. Okay, now we just recall what is IFS in Euclidean geometry or Euclidean plane. That is, let XD be a complete metric space if WNs are continuous maps from X to X. Then X together with WN n equals to 1 to n is known as an iterated function system. And if the WNs are contractive, then this IFS is known as hyperbolic. Okay, now similarly, that Barnsley defined what is known as real projective iterated function system. So here, instead of here, they have taken that space RP2 together with the maps that projective transformations, and they are uh, calling this as real projective iterated function system, or RPIFS. And they also proved that under certain conditions, this RFS generates an attractor. So we just quickly recall what is fractal interpolation function. So for that, a data point is given on that closed interval AB, and the data set is x and yn, and there are n contractive homeomorphism ln from I to in. In is that nth subinterval, and which satisfies the join up condition on, and it is uh, that is uh, that is contractive. And further, we assume that fn n continuous map satisfying the join up condition 3, so that it is Lipschitz with respect to that second variable. Uh, then if one define wn from I cross r to in cross r, where wn is defined as ln comma fn, then this map wn also satisfies the join up condition. Then Barnsley proved this following result, which is the main result for construction of that fractal interpolation function on Euclidean plane. That if let Ci be the space of all real valued continuous function on I endowed with that supremum norm, and consider the closed subspace C, y0, y, and I is nothing but all continuous function f which interpolates the endpoints. Then this IFS I cross r comma wn has an unique attractor G, which is the graph of a continuous function gi to r, which interpolates the given data points. And G is nothing but a fixed point of the RB operator T from CY0YN to CY0YN are defined by the TFX equals to Fn L inverse x comma f of L inverse x, x belongs to In for n equals to 1 to n. So this is some example of a fractal interpolation function. Okay. Now our construction of affine fractal interpolation function. So before construction of affine fractal interpolation function on RP2, uh, as we have seen for that Euclidean space, any graph that any function g from I to r, if that is a fractal interpolation function, then its graph x comma gx is a subset of R2. But there is no existing traditional way of um, a way to define that graph of a function f from P to RPN, where P is a subset of RPN, which lies on RPM for some m belongs to n. So for this reason, we first need to decompose that projective space, so that the graph lies on that projective space. Okay, so this is the decomposition. We have considered the space RP2 minus HE3. We have removed that hyperplane where E3 is 0, 0, 1, and we have defined two operation plus and dot as follows: that for x, y, z and x dash, y dash, z dash belongs to RP2 minus HE3, and for all a belongs to R, we one can define that xyz plus x dash, y dash, z dash equals to xz dash plus x dash z, yz dash plus y dash z, and zz dash, and axyz is nothing but ax, ay, az. So one may think that like in Euclidean geometry, for z equals to one plane, how the addition of 2 points and scalar multiplication works. From that, actually, one can think about this addition and scalar multiplication on RP2 minus HE3. Okay. like if you quotient by z, that x z y z1 and x dash y dash, x dash by z y dash by z and z dash and on, then how the addition works in that Euclidean plane, and for z equals to 1, that from that one can get motivation for this addition and scalar multiplication. So this was the first result, that under these two operation plus and dot, the space rp2 minus h3 now becomes a linear space, because rp2, that is not a linear space. So to define that factor interpolation function on projective space, on need that linear space structure of that space. So now we can we are uh, in a position to construct a factor interpolation function. So further things we needed. So from here, from this result, now one thing is clear, that any point xyz now can be expressed as x0z plus 0yz. So that means the space rp2 minus h3 is decomposed as a h on 0 plus h01, where h on 0 is nothing but x0z belongs to rp2 minus h3, and h01 is nothing but 0yz plus belongs to rp2 minus h3. H10, one can think about that all the lines passing through that xz plane, and h01 are the lines, all the lines passing through that yz plane. Okay. Okay, so for the existence of an attractor of a conductive RIFS, we need to define a norm on rp2 minus h3, for which the space becomes a complete nonlinear space. So we are defining this norm, which we are calling as projective norm, that is xyz norm p is defined as root over x square plus y square by mod z. Okay, so in Euclidean plane, if you think about it, for z equals to 1, that is nothing but the Euclidean norm. So this is the second result, that the space rp2 minus h3 is now complete with respect to this projective norm. Okay, so before going for further discussion, we need to introduce some more notations. That is, for x on 0 z on and x2 0 z2, 2 points in h on 0, we show that x on 0 z on is less than equals to x2 0 z on, if and only if x on z2 less than equals to x2 z on, and x on 0 z on strictly less than x2 0 z2, if and only if x1 z2 less than x2 z1. We have tried to give some order relation in rp2 minus h3 actually. So this is the definition of projective intervals on h on 0. uh, Let a10 c1 and a20 c2 belongs to h on 0 be such that a10 c1 less than a20 c2, then the projective interval on h on 0 is denoted by pi cross 0 and is defined by, it consists of all such x0z from h on 0, so that it lies in between a on 0 c1 and a20 c2. So this is the picture. Okay, so any line in between these two lines. Okay, so one may think that why we have not considered this portion, but that we cannot take, because if we take this portion, then there are lines which are on that xy plane, but that is not in that domain. So we cannot consider this side or this side. So this is the projective interval. Okay, now we consider that continuous function, all continuous functions on pi cross 0 on that projective interval, uh, and we take that non-sup norm here. Then the third result is that this space together with this sup norm is complete. So now we are ready to construct a real projective factor interpolation function through certain data points on RP2 minus H3. So for that, we have taken a set of data points in RP2 minus H3 xn, y, and zn such that xn zn plus 1 is less than xn plus 1 zn for n equals to 0 to n minus 1, and the projective interval pi cross 0 is nothing but x0z belongs to h10, so that x0 0 z0 less than equals to x0z less than equals to xn 0 zn, and the nth projective subinterval pin cross 0 is that collection of all x0z belongs to h10, so that xn minus 1 0 zn minus 1 less than equals to x0z less than equals to xn 0 zn for n equals to 1 to n. Now let n transformation that ln from pi cross 0 to pin 0 given by ln x0z as anx plus bnz 0z that satisfies the join up condition, and mod n less than 1, that's similar to that Euclidean settings. And we also consider n continuous map fn from rp to he3, rp2 minus he3 to h01 given by fn xyz equals to 0 cnx plus dny plus fnz comma z, such that fn satisfies the join up condition where the dn are the free variables. Then for n equals to 1 to n, we define the functions wn, uh, that is from rp2 minus h3 to rp2 minus h3 by wn equals to ln plus fn. Then if mod dn is less than 1 for n equals to 1 to n, then the RIFS is contractive, and hence by Banach fixed point theorem, it has an unique attractor G. Now one can show that G is the graph of a continuous function from that projective interval to H01. So for that, we consider that f equals to collection of all continuous function on that projective interval, so that it satisfies that that endpoint condition. Then that f is closed subset of CPI0 with sup norm, and so it is complete. So one can define that RB operator. Here actually we are naming it as real projective RB operator T from F to F as TFX0Z equals to Fn L inverse X0Z plus F compose L inverse X0Z, where L inverse is mapped from that IS projective subinterval to that PI0 and given by L inverse X0Z as X minus BNZ 0 ANZ for X0Z belongs to PI cross 0. Then the next result is that the RP operator T is well defined and contractive on F with so that projective norm. Sorry, this is that SOAP norm. Since this is complete by Banach fixed point theorem, it has an attractor, and we are naming it as that real projective factor interpolation function corresponding to that RPIFS RP2 minus HE3WN. So this is the main result, that the graph of the function f is the attractor of the RPIFS, and this is some example. We have done it for n equals to 4, and this is the data point for which this is the real projective fractal interpolation function, and with that scale vector dn equals to minus 0.3. If one can take that various means different scale vector, then to get this graph is little bit difficult, more difficult. Uh, and this is another example where we have taken dn equals to 0.1. See here that smoothness uh, is better to earlier on depending on that scale vector. And this is a means one highlighted thing that uh, this is a real projective fractal interpolation function, that left graph. And if you cut that graph at any plane, by any plane z equals to z naught, what you are getting, that is something looks like a fractal interpolation function on R2. So one may think that real projective fractal interpolation function is a pool of fractal interpolation function in R2. One can think of that, something like that. Okay, so these are some references. We have followed this article, that real projective iterated function systems, from where we get that motivation for constructing a real projective fractal interpolation function. And these are some projective geometry books on my use for reference. This is the article on this result. Okay. Thank you. Any
So,
questions?
thank you, Professor. Now, I would like to request to the audience if they have any questions. So, if there is no question for the speaker, so let's thanks the speaker. Thank you, sir. And now we'll take after 1 minute we'll have our next speaker.